Okay, let's talk a little bit about concrete. We definitely have some concrete graphs and information in the FE reference manual that we're going to need to know how to interpret. So plain concrete, it's going to have that high compressive strength, but little tensile strength. All right, so I can write that on here too. So high compressive strength, and this is probably something you're all very familiar with, but little tensile strength. And so here we are, strong in compression, weak in tension. Okay, and so because of that, we're going to do some things to help that concrete out. We'll talk about that in a minute. It is the opposite of steel, which is interesting because they're kind of partners there, right? Where steel is strong in tension and weak in compression. And that's why we use them together so often. So I'm sure you're familiar with that. When we talk about concrete mixes, we do them in this 1 to X to Y ratio. The first number is the part of cement by weight. The second number is some X I used here, part of fine aggregate by weight. And the third number Y here is the part of coarse aggregate by weight. So an example of this could be 1 to 2 to 3. Okay, we might have a concrete mix that's 1 to 2 to 3. That would mean 1 part of cement, 2 parts fine aggregate, 3 parts coarse aggregate. Okay, so that's a way you'll see that described. The strength of concrete is generally measured at 28 days, and we'll see a chart showing that here in a minute. Concrete also has some physical properties to it that are unique. One of those properties is called creep. Creep is defined as an increase in strain under a constant stress. Now there is in the reference manual, probably if you control find creep, that would take you to page 99 here. Let me get this out and show you what this looks like for creep. And there is a formula for creep. We're not going to go over it here, but it is here in this reference manual on page 99. So we've got creep here, a time-dependent deformation under load, usually measured by strain rate. And for steady-state creep, we do have a formula here. So know that that information is in the reference manual on that page 99. It is under this kind of mechanics of materials page, like I was talking about that modulus of elasticity. These are kind of the things that are going to be covered with Tom. So I'm not going to be covering too much on this page, but since I did mention creep, I wanted to point out that this formula is here for you if you are called on to calculate creep. So page 99 there. So it is an increase in strain under a constant stress. So it is different from, sometimes people get it kind of confused with a deflection, but remember a deflection does not have constant stress. So that's what makes this creep a different quality, is that the stress is constant there. And we can see that that's that strain that changes. So, here's our derivative. Remember that epsilon stands for strain. So change in strain over time, dE dt, d epsilon dt. One thing I'll say about this equation, again, we're not going to practice with it, and if you had to solve for this, you would be given these variables, but just remember things like the ideal gas law constant, and we'll do a problem like that today. Some of these things are in the beginning of the reference manual, so you can control find on those values if you don't have the ideal gas law constant memorized. So that is, I think it's like on page 2. Yeah, just to show you what that looks like. There's, on page 2 of the reference manual, there's a whole list of fundamental constants, and there is the gas constant here. They've got it in a bunch of different units. So you would see, to solve for creep, what's been given to you and what makes the most sense for you to use that gas constant. But you've got some other fundamental constants there as well. Just to point that out. Okay. All right, so that is creep.